Using the bootstrapping percentile method we've shown so far does come with some assumptions and does have some limitations. So first, here's a visual on the right, imagining that you have some population distribution here, which has some sampling distribution for a statistic. This is the sampling distribution of the sample mean for this particular distribution. Because I don't know what that looks like, all I can do is take a sample. So here's an example of one sample and the bootstrapped distribution of the sample mean that I get. And this is what I use to create my confidence intervals. For example, I'll take the lower 5th percentile and the upper 95th percentile if I say wanted a 90% confidence interval. Then I could do same process, get a different sample, and now I'm going to get a different 90% confidence interval. Same thing here, same thing here. So what I want you to notice is that each time that I get a new sample, the center of this bootstrap distribution shifts because it's going to be centered around whatever the sample mean is for my statistic. That's at least in the case here of where I'm doing sample means. We'll talk about it in the median or with the median in just a minute. But it's okay that this shifts because ultimately what I'm trying to capture with my confidence interval is a range around this statistic. And so ideally, this width here or my standard deviation that I'm capturing in each of these bootstrapped distributions mirrors the actual standard deviation of the sampling distribution. And in that case, each of these confidence intervals should have the same width, and they're just going to shift around where they're centered based on your sample statistic. Now, the quality of your bootstrap distribution definitely depends on the quality of your original sample, and so it's not the case that this will always work. Luckily, in each of these examples here, I'm doing a large enough sample size, roughly, and my samples pretty much mirror some of the trends that I have in my population, which is why these bootstrapped distributions all look pretty similar. Notice the bootstrap is not replacing or even adding to the original data, right? We're using it as a way to estimate the variation, the spread of the sampling distribution. For most statistics, this bootstrap distribution is going to correctly approximate the shape, spread, and bias of the actual sampling distribution. And that's what we see here. The one difference between this top sampling distribution and the bootstrap one is where it's centered. So the bootstrap distribution is centered at your original statistic plus any bias rather than the parameter value. But that's okay because that's how we design our confidence intervals. They're centered around our statistic value, and then we're really just using the width here to help get us the interval. I'm going to follow up on this idea of bias. So we introduced this in a previous video, and we said we define an estimator as biased if its sampling distribution is not centered at the true value of the parameter. So I pointed out that the sample mean is an unbiased estimator for the population mean. We proved that in a previous video. But unfortunately, for something like the median, there isn't actually an unbiased estimator that exists for the population median. So the bootstrap method is actually going to allow us to check how biased our estimator is as well by seeing whether the bootstrap distribution is centered at the statistic of the original sample. And I'll show you this in our notebook. We'll go back to this. But basically, a way to estimate your bias is to look at what is the expected value or the mean of your bootstrap distribution minus what is the actual statistic for the original data you're interested in. So let's go look at our median estimation when we did this previously, just to get a sense of the bias. Okay, so I am back in the confidence interval notebook, and we're in the we're actually in the bootstrapping the sampling distribution of the statistic section. So what I'm going to point out is what the bias is in our example. This is, let's actually not do the bootstrapped. So actually go up. I have us in the wrong section. Yeah, here's where we want to be. Sampling distribution of the sample median. If I have a completely unbiased estimator, then the mean of this distribution here will exactly equal the population parameter I'm interested in. So my population median is 136, 164. It looks very close to the mean of this. If I calculate the actual mean of this, it's 136, 218. So it's very small bias here. So I look at the difference between this and the population median. My bias is 54. We're talking, these are in thousands. I'm talking dollars. So, okay, let's start over. All right, so to get a sense of understanding a bias in a parameter, let's look at our median. We knew the population median value, it's here in green. And if you have an unbiased estimator, then the expected value of your sampling distribution will equal the population parameter. In other words, if I take the mean of the sampling distribution, I should get exactly back my population parameter. And we're going to see I get something very close. So my actual population median is 136,000. My sample median minus my my sampling distribution mean, which is like the way of estimating the expected value, is 136,218. So I'm actually only off by $54. That's a very small bias here, which is great because in general, we want very low bias. And how do I know this is small? Because I'm looking at total compensation and my scale here. I'm around 120,000 to 155,000. So a difference of 54 is very small on that scale. Now, how is that bias captured? Because I don't usually know this, right? A, I don't normally know the population median, and B, I don't normally know the sampling distribution of the sample median. So I wouldn't necessarily be able to calculate the exact bias. But I can see how my bootstrap distribution will estimate it. So I'm going to estimate that bias. If we come down here to estimate the bias, I'm going to look at what the actual statistic is for my sample. So our median compensation in my sample was 132,000. Then I'm going to look at, so that's roughly here, then I'm going to look at the mean of this bootstrapped distribution. So bootstrap medians.mean is 132,545, right? So they're pretty close. And again, the difference between those two is an estimate of the actual bias. The difference I have here, 128, that's an estimate of my real bias, which was 54. Now, it may feel like it's really far off, but again, looking at the scale of this stuff, that's pretty close. And again, that's still very small given the scale of all of this. So it is helpful in the sense that this bootstrapping method is helping me create a confidence interval, but also check for bias in my original estimator. Now, when should I not use this? So this percentile method works well when I'm estimating medians or means based on large random samples. However, it will not do well in the following situations. If I'm trying to estimate a min or a max or a very low or high percentile, then this percentile method is not going to do as great. My confidence intervals will not be on par with the percentage I'm expecting them to be correct. If my probability distribution of my statistic is not roughly bell-shaped, this percentile method isn't great. There's other ways you can create a confidence interval if you have more of a skewed distribution of a statistic, but doing the percentiles to get the lower and upper bound won't be the way to do it. And then if your original sample is very small, say less than 10 or 15, then the bootstrapped results are not good or not reliable because our original random sample so small that it's unlikely to capture the key features in the population. And that's what we saw in our last video, and we just played around with different sample sizes. So if any of those occur, this is not the way to go. And there are other ways to handle this one. And actually there are some ways you can handle super small data. It's just not in the scope of what we're going to show in this class. So if you are using the bootstrap percentile method, you want to make sure that we don't have these situations. Otherwise, your intervals are not going to be as reliable. And you can see a visual of that here. Here I'm using the bootstrap for a mean, but I have a very tiny sample size. My original population is actually pretty nicely distributed in that it's normal and symmetric. But you can see my samples are all over the place because I'm only taking 9, which means that my bootstrapped distributions are going to have widths that vary substantially. They're just going to be less reliable. So I won't be able to say, oh, I'm confident that 95% of these are going to contain the actual population mean on average, because there's just too much variability. All right, so recap of what we've just covered. Confidence intervals are our tool when we're trying to understand variability of our estimate. Ideally, if we had the population or we had the ability to go back and take unlimited samples from the population, we could come up with our sampling distribution of our statistic and capture that variability that exists around our sample statistic. But in reality, we don't know the population distribution and we usually can't take unlimited samples. So one method we use is bootstrapping, where we say, let's assume our random sample resembles the population, and then we're going to treat it as such and come up with a bootstrap distribution of our sampling statistic. We then use the middle X% of this distribution to calculate the X% confidence interval. The second method we can use is actually based on the central limit theorem, but I'm showing it to you second because it's not applicable in a lot of situations unless your central limit theorem applies. So we will get to that in a future video of how to do it this way. But I like to show you bootstrapping first because bootstrapping is actually more versatile and doesn't have the same restrictions.